is going to be speaking to us about.
I'll talk about first order theory of homeomorphism groups.
Okay.
Yeah. So some of you may have already heard some version of this already, and I apologize. I'll try and say some different things this time. So this is joint work with Sang-Hyun Kim and Javier de la Nuez Gonzalez, who are both now at Kios in Seoul. Okay. All right, so generally what I'd like to talk about is the group homeo of M here, where in general M is a compact manifold, and I'm not going to keep writing these subscripts all the time because I'll just forget to do it. So if we like, we can just write homeo 0 here. So I'm not interested in the group of components so much, but more in the identity component of this group. Okay, and so the connection to the topic at hand, so orderability of groups, of course, comes from the specific cases where M is equal to I and S1, and then of course countable subgroups of homeo 0 of M then corresponds to left orderable and cyclically orderable groups. Okay, so I said that I'd like to talk about the first order theory of this group, right? So all right, theory homeo 0 of M. This is the first order theory of homeo of M viewed as a group. Okay, so to give just a very quick explanation of what that is. So first order formulae or sentences in group theory, so which is what we're considering here, where the homeomorphism group is nothing more than a group. I'll call these well-formed statements. So I'm not going to make precise what I mean by this in the interest of time, and because I think the intuitively the meaning of what this is clear, in which any non-logical symbol is either the multiplication, this is the group operation, or the identity element in the group, and the variables and quantifiers range over individual elements in the underlying group G. Okay, so that's all I'll really say about logic. Okay, so then.
Sorry, but how does this form a group? You're saying you're viewing this as a group.
Homeo is a group.
Oh, you're viewing homeo as a group.
Yeah, so I can talk about it in this language of group theory.
I thought you were saying this theory.
No, sorry. No, the theory is just some set of sentences, right? So then you can write something like phi, a sentence, is in the theory of some group G if phi is a well-formed statement about groups, and phi is true in G. That is to say, in some precise sense, that sort of existentially and universally quantified variables are witnessed inside of G. Right, so the motivation, one of the motivations outside of the theory of, say, orderability, for studying the first order theory of some group, and in particular of homeomorphism groups, comes from the basic question of the degree to which the homeomorphism group determines the underlying manifold. Okay. So before I state a result, I'll give one more definition and then a background result. Okay, so if G1 and G2 are groups, then we write G1 three dashes G2 if G1 and G2 are what's called elementarily equivalent, that is to say, the theory of G1 is equal to the theory of G2. So, right, two groups are elementarily equivalent if, from the point of view of these well-formed statements which you can make about them in the language of group theory, you can't tell the difference between G1 and G2. Okay. So this is some equivalence relation on groups, okay, and it is refined by the isomorphism relation. Okay, so if two groups are isomorphic, then their theories are the same. That's some. I mean, it's really just an exercise in substituting names of variables in one group for names in another. Okay, so I can maybe just write that down. So G1 isomorphic to G2 implies G1 is elementarily equivalent to G2, and the converse is false. Okay, so there are famous examples due to Sella, where even for finitely generated free groups, two finitely generated free groups can be elementarily equivalent to each other and not be isomorphic. So there are examples due to Sella. There are many others. So now, with that sort of background foundation in groups and model theory, so what does this have to do with manifolds? Well, so there's a theorem from the 1960s due to Whittaker. This is probably the most straightforward way to motivate the main theorem that I'll talk about, which says that, so if M and N are compact manifolds, and for this theorem, and indeed for most of what I'm going to say, unless I specifically say otherwise, M and N can have no further assumptions on them other than compactness. So they can have boundary, and they don't have to have smooth structures. They don't have to have PL structures or anything. So if homeo 0 of M is isomorphic as a group to homeo 0 of N, then this implies that M and N are actually homeomorphic. And in fact, they have to be homeomorphic in a very specific way. So the homeomorphism, an homeomorphism between M and N induces the isomorphism between homeo 0 of M and homeo 0 of N. Okay.
And is that isomorphism between the homeomorphism groups as groups or
as abstract groups? Yes. Right. So no continuity in particular is assumed, and continuity falls out as a consequence.
And you're not assuming any of them are connected, for instance.
No. But I mean, they have finitely many components because they're compact. But other than that, No. Yes. Okay. So I just realized that this board doesn't move, so I made a strategic mistake here. Okay, oh well. So let's see. Okay, so I mean, there's a reason that I said something here about isomorphism being a stronger equivalence relation than elementary equivalence. So it refines elementary equivalence. Okay, well, for homeomorphism groups of compact manifolds, so it turns out that elementary equivalence and isomorphism are the same thing. So this is then I guess one of the main things that I'll talk about. I'll mostly talk about consequences of this. So this is by Kim Kardashian and someone else and Javier. This is not my joke. This was made during the workshop last week already. So okay. So we have that. So if M and N are compact, then homeo 0 of M being elementary equivalent to homeo 0 of N implies that M and N were already homeomorphic as manifolds. And in fact, you can say something stronger. So actually, there's a sentence, phi sub M. I don't want to use the existential quantifier because that suggests that it's a formal statement. So that there exists a phi sub M in the theory of homeo of M, such that phi sub M is in the theory of homeo of N, if and only if M is homeomorphic to N. So, right, so you don't need to check all the possible sentences about M and homeo N, you just need to check one. There's in particular one that asserts that for every manifold that asserts that I am homeomorphic to M.
You assume that M and N are manifolds in this?
Yeah. Always manifolds for this talk. It's I think in general for topological spaces, there's no hope of being true. No, they're not assumed to be the same dimension. Yes. So in particular, phi sub M implies that any N which has that in its theory has the same dimension as M. So so that's sort of the basic thing, the basic foundation for what I'd like to say in the rest of the talk. Okay.
So actually, when you say there's one sentence, actually, there are quite many sentences that they put all of them together. Right?
Yes, yeah, but I mean, it's you concatenate them and it becomes one. Yeah, yes. So, right. So just a remark, right? So this first thing that I said here, if homeo 0 M and homeo 0 N are elementary equivalent, then M and N were homeomorphic to each other. So that statement by itself, it can be called first order rigidity because homeomorphism groups are the only way that you can be elementary equivalent is if the underlying manifolds are homeomorphic. Okay. And this stronger statement is actually oftentimes called quasi-finite axiomatizability, because within the class of homeomorphism groups of manifolds, the homeomorphisms of a particular manifold are axiomatized by one sentence. So to not obstruct that, let me maybe continue over here. So make a few quick remarks about like the exact hypotheses that one needs on this theorem. So the hypotheses are a bit flexible. So I stated them for homeo 0 of M because to emphasize that this doesn't depend on sort of the discrete structure of homeo of M. It doesn't depend on sort of the mapping class group of M in any way. Everything is done in the connected component of the identity. And so you could replace, this group here on both of these groups by anything that lies between homeo 0 and the full homeo group. Moreover, you can look at other kinds of homeomorphism groups. For example, you can look at these things that what we called, I think is an appropriate name for them, are these Ox-Tobey-Ulam measures. So that would be a Borel probability measure on M, which has no atoms and gives positive measure to every open set and measures 0 to the boundary. Okay, so then you can look at the group of homeomorphisms preserving such a measure. So it's a theorem that any two such measures differ by a homeomorphism. So you push one forward by a homeomorphism, you get the other. So you can talk about the group of these Ox-Tobey-Ulam measure preserving homeomorphisms. And then you can actually replace homeo of M by homeo of mu. So just Ox-Tobey-Ulam measure preserving homeomorphisms on either of them, and any group in between the identity component and the full group. So that all carries through in a straightforward way. Okay. So I'm not going to talk too much about the proof of this. If someone would like to talk about it, we can talk about it later. But
So the theorem is for homeo.
beg your pardon?
The theorem is for homeo.
Homeo.
Then you say that it is also true for homeomorphisms that preserve the homeo.
Yes, that's right.
And what about the homeomorphisms that are absolutely continuous with the theta measure?
Good question. That probably works. There'd be a lot of things to check, but it almost certainly that's almost certainly rich enough. I suspect that this is true for like many classes of groups of homeomorphisms, like piecewise linear homeomorphisms of a manifold if you have a piecewise linear structure. So you just need that if you have a nice enough open set in your manifold, that the rigid stabilizer of that open set, that's to say the homeomorphisms that are the identity outside of that, is sufficiently dense in the whole homeomorphism group. So I don't want to write that down as a claim, but I'm pretty sure that's right. Okay. Great. So I'd like the rest of the talk that I'd what I'd like to emphasize or to sort of convey to you is that maybe this result isn't so surprising at all if you once one sort of sees how strong the first order theory of the homeomorphism group of a manifold is and how much it can say. So it can say a lot. So the first corollary of what I've said here is that so let M and N be arbitrary compact manifolds. So then homeo 0 of M interprets homeo 0 of N. Okay, so here interprets, I mean this in a precise model theoretic sense, so I can in fact tell you what that means in more directly. So what this means is that so there exists an N, so a natural number, such and a subset X inside of homeo 0 of M. Oh, I shouldn't have called it big N. Okay, let's call it lambda. I heard some murmuring and I thought that I maybe made one of these notational collisions. Yeah, okay. So there exists a lambda inside of N, a subset X inside of homeo of M to the lambda, which is definable. That is to say that it is cut out by a first order formula in the theory of groups. Right. So this is the way you can think about this is that pretend that homeo of M is just like the complex numbers, and then X is like an algebraic variety. So it's cut out by polynomials, except polynomials now are just formulae in the theory of groups. And a definable equivalence relation, E, such that homeo 0 of N is canonically isomorphic to X modulo this equivalence relation. So this equivalence relation again is supposed to just take 2 points in X, and it's just some formula that with 2 variables that says like this. So you plug in these 1 point for one of the variables, or really these are tuples of points, but 1 tuple for one of the variables and 1 tuple for the other variable, and the equivalence relation spits out yes if and only if they're supposed to be identified in this quotient. Right, so that you can, if you want to think about it in terms of something more concrete like algebraic geometry, then you can pretend that this could be like c. This thing could be like c to the lambda, and this is c to the lambda without the origin, and this is like projective space, or something like that.
Right, because isomorphism at the bottom. Is that an isomorphism like a group?
Of groups, yes, yeah, of groups.
So M could be a point, is that right?
So when I should say the dimension should be at least 1. Yeah, no, that's a good point. So I guess all of the yes, yeah, it's a very good point. So I mean, this would fail sort of at step 1 for manifolds of dimension 0, but so yeah, so the important thing is you need to be able to say things. So so the point is that when M has dimension at least 1, then homeo of M interprets second order arithmetic, which is basically the same thing as being able to talk about analysis. And so you can formalize within the group theory of homeo of M analysis. And in particular, you can talk about spaces being locally homeomorphic to Rn. And so you can formalize manifolds. Okay. And now, once you've talked about manifolds, you use this quasi-finite axiomatizability to say, I know which manifold you're talking about. So that's basically how that works. Okay. So maybe to make that slightly less abstract, I can say in more detail, like how homeo of the interval, for example, interprets homeo of the circle. Right? These are the homeomorphism groups that we like the most. So let's consider homeo 0 of I, right, which is isomorphic to homeo 0 of the real line, just by removing the endpoints. Okay, so we know somehow how to get homeomorphisms of the circle from this group, right? So we take an infinite order, fixed point free homeomorphism of the real line, right? And then you take its centralizer, and then you quotient out by the coset relation of quotienting out by the center. That's canonically homeo of S1. So you just do that, except inside of the confines of formalizing everything in first order logic. Okay, so I won't give all the details of this, so you have to take a little bit of it on faith. So there's a subset Z inside of homeo 0 of R, which is definable, such that F is in Z if and only if F is fixed point free. Right, so it would, I'm leaving compact manifolds, but really when I just mean fixed point free outside of the endpoints of the interval. Okay, so this is definable. Geez. Right, so this is not obvious, I think, but it is true. And what's more is if you look at the membership relation, maybe R sub F, so that maybe so G is in R sub F if and only if G is in the cyclic subgroup generated by F. I mean, in general, if you try and write, if you take a general group and you want to say, like, you take your favorite element, maybe that's even, you think of that as a parameter inside of your group, and then you want to write down a formula which is satisfied by some other group element if and only if it lies in the cyclic subgroup generated by that element. That's not easy to do and oftentimes not possible. But this is also definable. Okay. And so now what you can do is you have this group homeo 0 of S1 sub little f, which is given by taking the centralizer in of little f inside of this group, right? And then you quotient out by the coset relation of f, okay? And so then you impose a further, equivalence relation. So that's what I would call elimination of parameters, which I won't get into in detail, which allows you to get rid of this choice of little f's, to say that basically for any two choices of little f, you get canonically isomorphic outputs. You just get homeo 0 of the circle back. Okay, so that's a very hands-on way of understanding this corollary for the specific case where M is I and N is S1. Yes.
What's this so hard against your thing?
This is just the subset of okay. So this is what I mean by this is a unary relation, which is either, so you can think of that as just a subset of the whole group, right? So membership in this unary relation is, in some formal sense, this is supposed to be defined by a formula, right? It's true if and only if the semantic consequence is true, that the G is an element in the cyclic subgroup generated by F. Great, so that's one thing that one can do with this. Okay. But I'd like to talk about some more of the expressive power of did you have a question? Oh, no. The expressive power of the first order theory of homeomorphism groups of compact manifolds. Okay. So here's a theorem, and so I'll define the terms in this theorem after I write it. So just to be safe, I'll say here that suppose M is closed. So now and for most of the rest of the talk, to avoid some technical complications, I'll assume that M is a closed manifold. Then homeo zero of M interprets weak second order logic. So what does that mean? So that is to say that first, that homeo zero of M interprets second order arithmetic. So what do I mean by that? Well, this means that homeo of M knows what the natural numbers are together with addition, multiplication, and the order relation. But what's more is that it knows what subsets of the natural number are. So it also interprets the power set. And so then you can talk about things like, Dedekind cuts, and that's what allows you to talk about first order analysis essentially inside of homeo of M. And also it interprets what are called hereditarily finite sets. That's in homeo zero of M. Okay, so what is a hereditarily finite set? We'll write H0. So maybe just completely generally. So X, a set. Okay, so H0 of X consists of finite tuples of elements of X. Okay, so that's just, ordered n tuples for n completely arbitrary whose entries are elements of X. Okay. And H1 of X will be finite tuples of elements of H0 of X. Okay, so there's our finite tuples of arbitrary finite length whose elements are finite tuples of elements of X. So in general, you have H upper n consists of finite tuples of elements of H n minus 1 of X, and the hereditarily finite subsets of X, they're not really subsets of X. They really live in some countably iterated power set of X. This consists of the union of all for all n H and M X. So what does this mean in some practical sense? Okay. So I can write down for you a formula, which is simply a statement in group theory. Okay. And from that formula, from any element or from any tuple of homeomorphisms satisfying that formula, I can unpack in a canonical way elements in H of X. So the hereditary, I meant to write H of X is equal to this. It's the hereditary finite subsets of X. So I can unpack for you all possible tuples of homeomorphisms inside of X. Okay. So I mean, maybe that's just like, okay, well, so what? I mean, the consequences of this are more interesting than the sort of dryness of the statement of the definition of hereditarily finite sets and then the fact that you can interpret them. So as a corollary of this, so is the following. So there is a formula B of two variables X and Y, depending only on the dimension of the underlying manifold, such that for all G and H in homeo of M, in fact, you don't have to assume that they're isotopic to the identity. They're arbitrary homeomorphisms. We have that phi of G of H is satisfied if and only if G and H generate a group isomorphic to a free group on two generators. So that's to say that the locus of pairs of homeomorphisms that generate free groups is cut out by a single formula that depends only on the dimension of the underlying manifold. And there's nothing special about the free group. So you can replace F2 by any group with a solvable word problem. The basic reason for that is that so solvability of the word problem really boils down to having a Turing machine that solves the word problem, and Turing machines can be entirely encoded in arithmetic by the Church-Turing thesis, at least. So insofar as you believe in the Church-Turing thesis, this is true. So you arithmetize computation, and since we have not only does Homeo of M know what arithmetic is, it knows something much stronger. It knows how to do it knows how to do classical computation in any case, and so you can improve this corollary to arbitrary groups with solvable word problems. Okay, great. So what else?
How constructive is this?
Beg your pardon?
How constructive is this?
So in principle, these are completely constructive. Well, okay. So the sentences that that we produce for cutting out the particular homeomorphism group, that can be done very explicitly. So this hereditary finiteness is it's pretty explicit, but it's, as you can imagine, I mean, this is some sort of directed limit. So if you got pretty deep down into down the hierarchy, it would be pretty complicated, right? But I mean, in the end, if you have a given manifold and you had nice charts that you could write down in coordinates, then you would probably be able to even write down a formula like this. It would be very, very long, and it would probably have hundreds of alternations between existential and alternating quantifiers. But you could do it from we never do anything non-constructive. Okay, so the interpretation of hereditarily finite subsets of Homeo allows you to do things like encode tuples, right? So you can think of maybe I'll call it G upper bar is an arbitrary finite tuple of elements. Okay. So you can say a lot of things about the group generated by a tuple of homeomorphisms inside of Homeo of M. Okay, so here are things that follow. For instance, so there exist formulae P of a tuple, say of gamma bar for a tuple of variables to distinguish it from a tuple of elements, such that phi of G bar is true in Homeo of M, Homeo 0 of M, or maybe it's a Homeo of M, if and only if the following are true. For instance, so these are, what I'm going to write are different formulae for different properties, so they're not all the same formula. Like for instance, the group generated by the tuple G is amenable. Or G is infinite with property T. Or 3, that this group is locally indicable. Just a few examples. Okay. And so again, there's some dependence of these formulae on the manifold, but it's only on the dimension, right? So you can absolutely make one formula that works for every manifold separately. Okay. With a little bit of work, you can say, okay, this formula works for all manifolds of a fixed dimension. Okay. And then I don't know how to do it in general. I don't know how to make it true sort of universally. It may not even be true. I mean, I don't know. I'd be slightly skeptical if there were one formula which were true for 2 homeomorphisms of an arbitrary manifold, if and only if those homeomorphisms generated a free group. That seems a bridge too far, possibly. Okay. And so this local indicability suggests that some things about orderability might be detectable in purely sort of first order group theoretic ways. So for instance, you can do the following. So let G bar be a tuple of elements in homeo 0 of R. Okay, so there exists a formula phi. I keep calling everything phi, so I'll call it maybe I'll decorate it by something like phi con. If such that phi con of G bar, if and only if the abstract group gamma generated by this tuple admits a Conradian left ordering. So something like that, I mean, something like that is possible to write down. Whether it's useful is a separate question, and maybe I'll use my remaining time to comment on that. Right. So, okay, I mean, we have these various formulas. So maybe you could be like, well, so why don't you get this formula for the circle, right, and ask a computer if there exists an infinite group with property T acting by homeomorphisms on the circle. But that's just simply not going to work. And there are many reasons. So the basic one is one that I've mentioned already, namely that homeo of a manifold interprets arithmetic. Okay, and so right, Gödel's first incompleteness theorem implies that the theory of homeo of M is not decidable. Okay, so there's no hope that you can write down some sort of algorithm which will enumerate which will evaluate all statements about homeomorphism groups as true or false, unfortunately. Well, I mean, if there were, I mean, I think things would be a little bit too simple. But there are things that are even worse about homeomorphism groups of manifolds. I mean, so I guess, and if one, right, so this first incompleteness theorem is something special about the first order theory of arithmetic, and so that we try and talk about arithmetic with these compact sort of semantic pieces, and I mean we need to have some way of knowing that like one way of talking about the natural numbers is the same as some other way of talking about the natural numbers. Okay, and so once you formalize some axioms, you can be sure that like the things that I prove are the same things that you prove. But then, right, so that already causes some problems here with trying to determine truth inside of this theory. But the truth in this theory is even more elusive. Right, so here's a final proposition, is that so there exist sentences in group theory whose truth in homeo of say a manifold M are independent of ZFC. Okay, so in particular, what you say to be the theory of homeomorphisms of a manifold depends on what you assume about set theory. Okay, so I mean, usually when you have some sort of you can have like some axioms for some class of structures, or you can like axiomatize piano arithmetic, right? And then you have many different models for it, right? So there are models which are like the standard model, which is what we sort of always assume that the natural numbers are. There are like non-standard models, but once you fix the natural numbers, then you can talk about like all the things that are true about the natural numbers, and that's some sort of complete theory. Well, I mean, inside of ZFC, which is where we do most of our mathematics, there's no complete theory of homeomorphisms of manifolds. So what the theory is itself depends on what you assume about set theory. So I think this is maybe a good place to stop.
So again, I mean, these formulae, I mean, they're constructed.
Yeah, they're constructed. Yeah, so for instance, like, I mean, it's because you have this incredible power in talking about like arbitrary tuples of elements, right? And so then you can, when you can talk about tuples, and then if you can write down a formula which is true for a triple of elements F, G, and H, if and only if H is F times G, then you can do an unbelievable amount of stuff. Yeah, and then like for property T, like there's this characterization of property T within the like real group ring of a group that's due to Ozawa, that you can just encode that inside of a homeo of M.
So even if there was some, I mean, even if the theory is undecidable, it might still be true that for some formulae.
Oh, yes, that's probably true, but I suspect that might be a fairly limited class of formulae. So I'm not, or sentences. I'm not sure which ones, but it's a good question. Which ones? Yeah.
You don't know that any of these are definitely not decided.
I do not. No. No, it would be cool if you could encode the amenability of F, for example, as an undecidable formula. Yes. Or independent of ZFC, even better. Yeah.
Any other questions? Let's thank the speaker again.